All right. Thanks, John. So, who are the optimisation group? This is us. So we sort of come into sort of some subgroups: discrete optimisation, energy optimisation, heuristic search, bioinformatics, and XAI. And we've got two new members. Terence Mack just arrived, who's both in energy optimisation and discrete optimisation, and Marcus Wagner arrived at the end of last year. So I'll count him as a new person as well. And sadly, we lost Mark Wallace to retirement. So that's our current group. So the way I interpret this is that I want to tell you basically about some of the research we're doing. So there's the BOAST slide. The only thing that's really, and I'm trying to shorten the time here for Mario. So I'll only say that the really great thing has been having sabbatical visitors back. We've already had 6, I think, and in fact Lawrence Park is visiting us now. And we have to organise a talk for him to talk to the faculty about what he does. All right, so let's talk about research directions in our group. So Optima is not really a research direction, but I have to talk about it because we still have scholarships and we want you to, if you've got some potential industrial clients, come and talk to us. Discrete optimisation is kind of the core of the group. Energy optimisation is a critical application of what we do, and of course we've got Ariel in our group who leads the Monash Energy Institute. Heuristic search, led by Daniel, is an incredibly powerful group in that space. We have Harun running bioinformatics. We're a big impact from a very small group. And we do XAI, and I'll talk a little bit at the end about election auditing, which I love. All right. So what's Optima? This is this ASC training centre in optimisation. And the main reason I'm putting up here is that we still have scholarships available. So if you have an industrial partner out there with a problem which has an optimisation component, then please come and talk to me, because if we can make them an Optima partner, then it's only 100K for them, and they'll get a whole lot of added benefits of being part of this large optimisation group, which is really has experts in all areas of expertise in optimisation, and is doing exciting things, and will give a lot of value add to your PhD student, a lot of training opportunities. Okay, but the discrete optimisation is kind of the core of the group where we focus. This is discrete optimisation, and really the centre point of that is Minizinc, which is our kind of modelling language, which has been around for a while now. It's very widely used around the world, so we're very lucky that we have a software system which is actually used by industry as well as academia to solve a lot of real-world problems. And this is one of our core things that we focus on. And you know, the kinds of things we're working on now is make it incremental. So many times you solve not just one optimisation problem, but a series of very closely related optimisation problems. So having an incremental ability from the modelling language level will allow us to do that much more efficiently. And another thing we're working on is richer type language. So everyone's loved dynamic types, and now they've realised the pitfalls of those, particularly in optimisation. If you make an error, what happens is your model runs for 100 hours and gives you no solutions. It's not very easy to debug. So having a richer type language to make sure that it's harder to write bugs in your model, so the types are checking things, is very important, and that's one of the other things we're working on for Minizinc. And of course, a lot of what we do is we solve optimisation problems with partners. All right, let's talk about energy optimisation. Energy optimisation is absolutely critical. We should all know this. Basically, the energy infrastructure of the whole world has to change very rapidly now, right? To go from this centralised thing where we have big generators to where a lot of the energy is extracted or comes into the system from the edges, and we have batteries and all kinds of things that are going to change the whole way the energy works. And the energy optimisation group is tackling those kind of problems. Good thing is that they have this so much, everyone knows that this has to change. Every company in the energy space has problems that they don't know how to solve. It's a really great time to be doing energy optimisation because there's such big problems that have to be done. And just to show off some of our new people, so there's this ARPA Energy, that's basically American Department of Energy, runs this competition, $3 million US prize money, and Terence Mack, who's one of our new hires, is actually building instances for that. So we're playing in the big big boy space. Of course, him generating the problem instances means we can't compete, which is a great pity. We would love those $3 million, but there you go. And also Marcus Wagner, who's just joined us, is the local chair for Gecko 2024, and that's one of the big optimisation conferences which will be in Melbourne next year. So if you're interested in learning more about evolutionary optimisation, then certainly come along to Gecko. And we have other parts of energy, so this ongoing project with Woodside. We have a long-term collaboration with Woodside led by Maria. And this is great because we've built this trust over the time. And some of the things she was talking about today earlier is really because we have this partner we've been talking to a long time, and we've seen how they react when we give them an answer to their optimization problem. And it's not like what we hoped. You know, look, here's the answer. They go, hang on, that doesn't make any sense. They want to be able to understand, they want to be able to debug, they want to be able to fiddle around, and that leads to all the problems that Maria was talking about earlier. But the new problem they're working on is this hydrogen supply chain optimization, so planning where to build hydrogen infrastructure. It's a great part of this new energy infrastructure that we have to do. Very complicated stochastic optimization problem, right? Many unknowns. That's why you need this diversity. You need to explore solutions, all that kind of stuff. Let's talk about the heuristic search group. So one of the things that they do is this multi-agent pathfinding. So this is the baseline problem for getting multiple collaborating robots to move around without hitting each other, right? So basically we have a whole lot of robots. They've got to go from their start location to their end location, and then I'll let them run into each other. So it's a critical part of any kind of multi-agent robot system. And we are clearly world leading in this space. All of the optimal approaches were developed here. The CBS approach existed, but we improved it by orders of magnitude. The other two were developed here. So we've won the last two flatland challenges. I should say that all of this work, a lot of this work is in collaboration with University of Southern California. And I'll show, I'll steal some more good from them. So we're well ahead in this optimal space, which is where you actually find the best possible solution. But in the real world, we often need to just find good solutions quickly. Right, so this flatland challenge, we didn't find optimal solutions. We were able to find good solutions quickly using large neighbourhood search. And our current challenges are trying to extend that approach to scale to bigger and bigger problems. And that's using PIBT, which is currently the most scalable non-optimal approach, and extending our things to more complicated versions of this, so multi-agent pickup and delivery, where now we're actually having our agents pick up and deliver multiple things at different times. So one of our key goals in this is to have a better engagement with Amazon, because Amazon, of course, solve multi-agent pathfinding problems all the time. That's what's happening in their robotic, what are they called? Facilitation centers? I can't remember. Got a funny word. So we have, Daniel's managed to get some, we've had multiple faculty research awards from them. Daniel's managed to get them to fund this MapF competition that he's about to run. And we've been talking to Amazon Air, which have a very interesting MapF problem about when all their drones are trying to land a particular thing and fly out at the same time. So you basically get a problem which is so complex in terms of number of things that it's no longer air traffic control. Those sort of methods don't work when you have hundreds of drones coming in and out, right? So we need to treat it as a MapF problem. And here's the glory we're going to steal from USC. So Jo Young Lee just won the ICAP's Best Thesis Award. Now, she's a USC student, but half of her chapters in her thesis are co-authored by us. So a lot of the work, she worked with us, and she actually ended up spending a year here. She came for a 3-month visit, and then lockdowns happened, and she was here for quite a long time, which was great for us because we get to spend a lot of time working with a very talented student who's now a professor at CMU. All right, let's talk about bioinformatics. So as Jeff mentioned, MML comes from here. This is Chris Wallace's things, and it goes on both in the optimization group and the machine learning group, where we use an MML approaches basically to tackle bioinformatics problems. And really it's Arun Konagurthu who's doing this, and he's managed to generate this very strong set of software which is used very frequently. So Mustang is one of the most widely used multiple structural alignment tools in the world. Pro-origami, which is actually building protein 2D diagrams, which are just used for explaining how protein structure looks in a 2D space, ends up being used for all these Cell and Nature publications, which is nice, even if itself is, only in a little minor journal. And things like SST, secondary prediction tool, this is tool developed by Arun, was actually one of the tools used for building AlphaFold, right? So this is obviously stuff, so AlphaFold is the best solution we have to the 3D structure prediction problem, and it's making use of our tools, so that's great. Currently, we're developing this Rotamer library. So what's a Rotamer library? Basically, when you have a protein structure, this is one individual peptide, then there's a relationship between all these angles, the phi, the psi, chi1, chi2, chi3 are all the side chain angles. So this determines what are the possible structures of an individual peptide in a peptide chain or a protein. So it's one of the sort of fundamental tools for understanding possible structures of proteins. So this Dunbrack Rotamer library has been out there for a long time. It's very widely used. We've just developed an MML-based version, which is both more accurate and more concise and actually allows more usages. So we're hoping to see that essentially replace the Dunbrack library because it's just a better way of doing the things. Rather than bucketing things, actually do it with some principle. Another thing we work on is explainable AI, and so now here maybe I'll get some tempers raised so we can get some good questions. We know that decisions made by machines have to be explained, right? There's legal things happening in the world to make that the case. And it turns out that most of the approaches that you read about XAI, explainable AI, are wrong. They're heuristic methods. They say, oh, we look in an epsilon ball around this thing and we make some assumptions, we'll do a lot of probing. They give you just wrong answers. So basically, most of them are utter garbage. So in order to actually have a correct explanation, you have to formally reason about the thing that you're saying. If you want to say the only reason why this machine made these decisions is because of your age and your income and your thing, then you have to prove that they are the only reason, not something else. In order to do that, you need formal reasoning, and that's what we do in our XIA. And the challenges, of course, here is scalability. There's no way you're going to get formal reasoning about a large language model, right? So if you want to use a large language model to explain a large language model, you can, but it's just going to be garbage in, garbage out. So Alexei Ignatieff leads the world in developing these effective formal AI approaches. And one thing so there's plenty of posters out there. You can talk to him about this kind of stuff. So you can look at the posters to see some of the things we're doing. But one of the things I'm very proud of, which we've just submitted to NeurIPS, is this first formal approach to feature importance, where we can actually have a crisp definition of feature importance, which has an exact definition. It can be exactly computed. And we have, of course, because it's very hard to compute exactly for real-world problems, we have a way of approximating that quite effectively in practice. So I'm very proud of that kind of stuff that we're doing in the explainable AI world. And finally, something I want to talk about, because you won't see anything about it in the posters anywhere, because there are no A-star venues for this work. Right? There's a little niche area called election auditing, which is a combination of combinatorics and statistics. And it may end up being one of the highest impact things that we end up doing, in the sense that this is actually a very important thing, particularly in the US, where clearly elections are completely fraught. They have the worst electoral system because, for example, the governor of the state is the head of the electoral commission for his own election, or his or her own election. You can see how clever that is. So they add auditing. So we after the election, we go through and check that the result that was reported is likely to be the correct result. Yeah? And it's mandated in 15 states in the US. It's increasingly mandated around the world. We developed the first method for instant runoff elections. So instant runoff voting elections are our lower house elections, right? Where you have a ranked choice and people get eliminated until someone has more than half of the votes. And we've just developed some new, more efficient methods for doing that. And this is one of the few cases where we have like pull research. We have electoral officials in the US talking to us saying, please, can you develop a method to audit 2 to 3 seat single transferable vote elections? Because 2 to 3 years from now, we're meant to be running audits for these things. And there is yet any actual method to do that, right? So this is a thing where the auditing sort of demands that they put into their legislation saying, before 2027, you must be able to audit this election. There's actually no method out there. So for us, it's very interesting. And yeah, we have lots of electoral officials talking to us. In fact, Michelle Blom, who's at Melbourne Uni, who's the chief implementer, is doing a whole lot of contract work, actually building auditing systems for various electoral places in the US. Okay, so what I was trying to give you was an overview of some of the things we do in the group, and some of the newest things that are happening. You can certainly look at the posters out there to see, other things that have happened in the last 3 years, so you have an idea what we're doing. But basically, I want to say this. If you have an optimisation problem, come and talk to us, right? We love to solve optimisation problems, and most optimisation problems have some other part to them, right? We do a lot of work in this combination of prediction and optimisation, where clearly we have machine learning as half of what's going on. So come and talk to us about it, and we'd be very happy to work with you. That's it.
Thanks, Peter. That was great. We've got time for 1 or 2 questions, if anyone would like to press Peter on some of those points he blithely made.
Yeah, thanks, Peter, for the nice talk. So I'm particularly interested in this XAI part. So can you elaborate a bit more, like how you guys XAI work can be applied to explain ChatGPT?
No, it can't be explained. No one will explain in any formal way ChatGPT, right? No one will explain any deep neural net. It doesn't have to be as big as ChatGPT. There's no way you can reason about a thing with 100 million variables in it formally, right? And so that's why I'm sure there'll be millions of papers still on XAI approaches where we use ChatGPT to explain ChatGPT, right? But this is just garbage in, garbage out, right? We know ChatGPT makes up garbage, as we just had Jeff's example. It'll make up rubbish to support whatever you want. And then you can use it to ask itself why it did something. It'll make up some other garbage to explain why it did that. So XAI, one of the things for XAI, and one of the things we look at is decision trees, things like this, are actually, you can come and see my poster tomorrow, these are explainable, they're small, right? Now, if you build decision trees, they're bad if you build them greedily, but if you build them optimally, they're actually fairly good, right? You've sort of built in Occam's razor. If you try to build the sparsest decision tree to explain something, then Occam's razor is being done in, and you're going to get pretty good test accuracy, even with the small tree, because you're actually optimizing, you're using Occam's razor essentially, which is a good way of, it's the MML idea, right? Don't make something which is too big to explain what you're doing, it'll overtrain or overfit. So I think the challenge for all of us is we need to go to smaller sort of versions of explainable ML models. Boosted trees are a good example. They're not too difficult to explain, right? And they can be very accurate, and they can be state-of-the-art for many ML kinds of activities. We're never going to explain large language models. We're never going to explain deep neural nets, because the size that we're talking about is just beyond what formal reasoning methods can do.
Yeah, but there's such a need in practice there. Yeah,
so, and you see these epsilon ball ideas, but where you say, as long as you're very, very close to what we did here, so if you change these pixels by this amount, you're still guaranteed to get the same solution, right? And so there's a lot of work in this sort of space. But how meaningful is that? It's not very meaningful to say, if I give you an image and you're allowed to change 13 pixels by 5% of their RGB values, that we're going to get the same image. Is that an explanation? Not really, right? So
fantastic, Peter. I'm going to let you wrestle Jan Fay over lunch after photos.